Okay, now we are going to do two examples for the three-phase transformer, but this is the example number 7 in this course. Now, the example says that we have one phase, 50 kilovolt ampere, these voltages, 60 hertz transformers. So we have three separate single-phase transformers with these rated values for them, and are connected to form a three-phase 400-230 volts transformer bank. So we connect them in a three-phase, and we connect it in a three-phase so we can get this rated voltage for the given three-phase transformer. The equivalent impedance of each transformer, referred to the low voltage side, is 0.012 plus J 0.016 ohms. The three-phase transformer supplies a three-phase 120 kilovolt ampere, 230 volts, 0.85 power factor lagging load. It doesn't, the book doesn't, the example doesn't say it's a Y delta connection, but I'm gonna say forward that it is a Y delta connection. For A, draw a schematic diagram showing the transformer connection. For B, determine the transformer winding current. C, determine the primary voltage line to line required. And for D, determine the voltage regulation. So it's a Y delta configuration. Why? Because as you can see here, it's 4,000 volts or 4,000 volts. How do you say it? I don't really care. But these three-phase transformers, on the primary side, the rated voltage is 2300 volts. So, but this is for the phase voltage, not for the line voltage. So this is a line voltage, and this is a 230 volts on the output. So, on the primary side, we will have a Y connection, like this. So this is for A. So over here, we have to have 2300 volts. So this is the phase voltage we want. This is not the line voltage, but the line voltage is 4,000 volts. So if you want the phase voltage in a Y connection, the phase voltage is the line voltage . So the line voltage in a Y connection, this is for the Y connection, the line voltage is the phase voltage times the square root of 3. So the phase voltage over here is the line voltage divided by the square root of 3. The line voltage is 4,000. And that is equal to almost equal to 2,300 volts. So that is why the primary side is Y connection. Here we have current I1. Because the rated voltage is the same for one transformer, as you can see, 230 volts. So that is why we connect the primary side of a three-phase transformer to Y connection. Now I'm gonna So that's the primary side. I hope you understand why the primary side of a three-phase transformer is in a Y connection. Now the turns ratio for all of these transformers is, we can look at their rated voltages, and the turns ratio is 2300 divided by 230 volts. And that is equal to 10. And now, the load here on the output says it needs 230 volts. So look at now this situation. I have a delta connection, and the induced voltage over here is V1 divided by A. And here I have a load that is 120 kilovolt amperes, 230 volts, and 0.85 power factor. Like it, of course. Now, the phase voltage and the line voltage is the same. So if this was a Y connection, it wouldn't be the same. It would be V1 times square root of A. So if we have V1 divided by A, that is 2300 volts divided by 10, that is equal to 230 volts. The phase voltage is then equal to the line voltage. And the load, the required load on the output is 230 volts. So that's why we have to have this in a delta configuration. The voltage in the phase is A1, but the line voltage is square root of A times I. Let's say this is voltage IS. The secondary voltage, this here is I2, and this here is I1. Okay, so this is the schematic diagram showing the transformer connections. So that is why we have Y delta configuration. Okay, now we have, for B, determine the transformer winding currents. Now, this is a delta load, and the apparent power, S, capital letter S, is equal to 3 times the line voltage times the line current. So if you don't know this, you should look at the fundamentals of electrical engineering, and this is because every let's say this is the load. Don't look at this as a transformer. This has apparent power if it's a balanced load, in which this case is this. This is the balance, the same load as here, and this is the same load as here. Now, square root of 3, sorry. the apparent power of one phase is equal to the phase current times the voltage. Let's say S1. That is the phase voltage times the phase current. The phase voltage of a delta connection is the same as the line voltage. And it is the same as, and the line voltage, the phase voltage is equal to the line voltage divided by square root of 3. I apologize for this huge mistake. So the line voltage divided by square root of 3. Now the phase voltage is equal to the phase current is equal to the line current to the divided by square root of 3. And we have the one load on the delta connection, the second and the third. Now the equivalent load is the sum of these two apparent power. The equivalent apparent power is the sum of these three apparent powers. And area of this is the same. So the equivalent apparent power is equal to this. Don't look at this to the right. So S is equal to, we have 3 times VLL, ILL divided by the square root of 3. So that is equal to 3 times VLL ILL divided by square root of 3. 3 divided by square root of 3 is equal to the square root of 3 times the line voltage times the line current. So if you didn't know this, I hope you know now. And that's how we are going to calculate this line current here on the secondary part. So the parent power on the secondary side, this is S is secondary, is equal to square root of 3 times the line voltage on the secondary side times the line current on the secondary side, which means this IS is equal to this IS. The apparent power or the apparent load on the secondary side divided by square root of 3 times the line voltage. Now, it says here that the load is 120 kilovolt amperes. This is the apparent power, so this is equal to 120 kilovolt amperes. But I'm going to write like this. divided by square root of the line voltage, and the line voltage here must be equal to 230 volts. And that all is equal to 301.24 amperes. So this is the line current on the load. Now, what is the current in the phase of this delta configuration, I2? Well, I2, the phase current in the delta configuration, is the line current, of that comes into the delta configuration divided by the square root of 3. So the I2 must be equal to IS divided by square root of 3. It doesn't need to come in, or it can go out, as in this particular situation. So this is the phase current of this transformer on the secondary side. That is equal to 301.24 divided by square root of 3. And that is equal to 173.92 amperes. And what is the current on the primary side? Well, the phase current and the line current is the same. And by this formula, I2 is equal to A turns ratio times I1. So I1, primary current, is equal to I2 divided by the turns ratio. Which is logical, because if you have higher current on the output, you have lower current in the input on the primary side. And that is equal to 173.92 divided by 10. That is, well, they wrote it like 17.39 amperes. So this is the current on the primary side. So we solved for B the winding currents. Now we have to determine what would be the primary voltage required, so that this here is 230 volts. It isn't exactly 2300 volts, or 2300 volts, because we have an impedance that is on the lower side, but we are going to refer it on the high side, higher voltage side. As we did this, now this is the same as we did on the single phase transformer. Now I'm gonna remove all this because I don't need it anymore, but you will have it in your notebook. This all was for B. From A, here, 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 and here. This was all for B. This is now really important to understand these three-phase systems, because induction motors and synchronous machines all are, 99% are all three phases. So it's really important to know the relationship between parent powers, the delta Y configurations, and so on. Now, this is like the single. Now we have a single phase transformer. This here is the impedance on the low voltage side, on the secondary. But let's refer that to on the higher voltage side, and you remember how we did that. That the Z equivalent on the high voltage side is equal to Z equivalent on the low voltage side times the turns ratio squared. So the equivalent impedance looking from the high voltage side is going to be equal to 0.012 plus J imaginary number 0.016. All that A squared, A is 10, so we have times 10 squared. When you do all this, this is equal to 1.2 plus J 1.6, all this in ohms. So this is the equivalent impedance looking at it from the high voltage side, where we did it in my previous videos. Now the rest is really easy. The power factor or the phase angle phi is equal to the inverse of cosine times the power factor, which is 0.85. That is equal to minus because it is lagging, so we have to say minus. Oh no, it's not. For this is not. We just need to know the angle. When I put it on in the current, we will have to use minus sign. But this is equal to. We just have to know what is phi, and this is equal to 31.8 degrees. Okay, now how does this look? Well, and of course, if we are transferring all from the low voltage to the high voltage side, then V2 prime, so this is the referred low voltage side on the high voltage side, is equal to A times V2, and that is equal to 10 times 230, that is equal to 2,300 volts. Now we have the next particular situation. We have resistance of 1.2 ohms. We have this inductance, which is equal to J16, 1.6 ohms. Now if we refer it to the high voltage side, then we have current I1, but with the lagging load of lagging power factor of 0.85, so we have the current 17.39 amperes with the phase angle of minus 31.8 degrees, and the referred low voltage side on the high voltage side, which is equal to V2, that is equal to 2,300 volts. Now we have to calculate what is V1, what is the primary voltage, primary line-to-line voltage required, so that we will have an output of 230 volts but this is just referred to the high water side. We did this already in my previous lectures. So the V1 is equal to 230 volt, 2300 volts, and this is zero phase angle. So I can write like this. So his angle is 0 degrees plus 17.39 minus 31.8 degrees times the impedance, which is equal to 1.2 plus J 1.6. And we are going to see what is the, firstly we are going to see what is the phase angle, and we are going to calculate easily what is the line. Angle voltage, and we are going to easily calculate what is the line-to-line voltage on the primary side. We did this for easier computations. So because this is the this is 0 degrees, it doesn't have an imaginary part. So this is equal to 2300 plus, now 17.39, and in brackets I'm going to write down this like this: cosine of minus 31.8 degrees plus imaginary number times the sinus of minus 31.8 degrees, and I'm gonna multiply all this with with the impedance of the transformer referred to the high water side. I'm gonna write this down. Well, cosine of minus 31.8 is 0.85. That is easy. Plus sinus of minus 31.8. You have to use your calculator for that. And it is equal to minus 0.52, but I'm going to write like this, because plus and minus gives minus. This here plus is it then becomes minus, and that is equal to what? Don't forget this imaginary number. So this is the imaginary part of the primary current times 1.2 plus imaginary number 1.6. Now I need to make some room. Now I'm gonna continue here. But of course in your notebook you go below. 2300 plus, I'm gonna write 17.39. Oh. There's still some alcohol on the whiteboard. Now I'm going to multiply these two brackets. 0.85 times 1.2 is equal to 1.02. Zero 0.85 times 1.6, but don't forget the imaginary number. Sorry, these gloves for coronavirus are a little bit nasty. So this is equal to plus j, which is imaginary number, 1.36. Okay, now minus j times 1.2 minus j 0.526. In my country, we usually write comma instead of dot. And this is equal to minus j 0.631. Minus j times j is minus j squared. And minus j squared is equal to minus 1. And then j squared is equal to minus 1. And minus 1 times minus here, you get plus. I think you know that from mathematics. So this here will be plus. This here will now be a real number. It won't be an imaginary. So I have to just calculate 0.526 with 1/6. And that is equal to 0.841. Okay, I'm gonna write this down. Now 1.02 plus 0.841 is equal to 1.861. 1.36 minus 0.631 is equal to plus j times 0.729. Now, I have to calculate the real parts, and I have to multiply this with this and this with this. 17.39, which is magnitude of the primary current. This is equal to 32 times 3/6. When I multiply this with this, 17.39 times 0.29 plus j 12.67. And this is all equal to 2332.36 plus J 12.67. So if we want a pure 230 volt output with all those currents that we calculated on the phase voltage on the primary side, we have to bring this Now, this isn't very nice, so we are going to calculate the magnitude and the angle of the phase voltage. So the magnitude V1 is, this is magnitude, is equal to the square root this squared with, Pythagoras theorem plus this squared. Let me just calculate this. And I get 2332.39. And the angle, let's say theta, is equal to the inverse operation of 12.67 divided by 2332.36. And that is .31 degrees. So this is the phase angle, and this is the this is the phase angle of the phase voltage, and this is the magnitude. Now, because on the primary side we have a Y connection, it says what is the primary voltage line to line required. Well, this was the phase voltage, so we have the line to line voltage is equal to square root of 3 times this. I am really sorry that there was 3 more, and that's 23,332. And the required line-to-line voltage is equal to, on the primary side, 4,039.8. So it's a little bit more than the rated voltage. Now the voltage regulation, VR, so this was for C. And for D, the voltage regulation, that is really easy. It's equal to V1 minus V2 I hope you remember the formula. That is equal to 1.41%. Which is okay for the lagging load. So that's it, and see you in my next video. I'm going to do one more example for the three-phase transformer. Goodbye.